height in my bio from 6'3" to 6'4". I've since removed my height entirely, but this is a complete lie. So normally it'd be hard for me to prove that something didn't happen, but luckily you can literally Google my height. If that wasn't enough proof, like Dr. Nagar said, then here is my freaking driver's license. Hayden, my birthday, 6'4". I don't know why I have to prove this. Now, I really wish the lies had stopped there. After he made his second video, and I made a video response to that. Do you have erectile dysfunction, or are you just insulin resistant?
Goal from generating new text. Text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then tend to land on vectors that are some very high-dimensional space. Words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron, or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multilayer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt, and then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multilayer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini
multi-context
series about deep learning. And it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple decades have proven to scale remarkably well. What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be formatted as an array of real numbers. This could simply mean a list of numbers, it could be a two-dimensional array, or very often you deal with higher dimensional arrays, where the general term used is tensor. You often think of that input data as being progressively transformed into many distinct layers, where again, each layer is always structured as some kind of array of real numbers, until you get to a final layer which you consider the output. For example, the final layer in our text processing model is a list of numbers representing the probability distribution for all possible next tokens. In deep learning, these model parameters are almost always referred to as weights, and this is because a key feature of these models is that the only way these parameters interact with the data being processed is through weighted sums. You also sprinkle some nonlinear functions throughout, but they won't depend on parameters. Typically, though, instead of seeing the weighted sums all naked and written out explicitly like this, you'll instead find them packaged together as various components in a matrix vector product. It amounts to saying the same thing. If you think back to how matrix vector multiplication works, each component in the output looks like a weighted sum. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters that transform vectors that are drawn from the data being processed. For example, those 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices. Those matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories to understand what that type does. As we go through, I think it's kind of fun to reference the specific numbers from GPT-3 to count up exactly where those 175 billion come from. Even if nowadays there are bigger and better models, this one has a certain charm as the first large language model to really capture the world's attention outside of ML communities. Also, practically speaking, companies tend to keep much tighter lips around the specific numbers for more modern networks. I just want to set the scene going in, that as you peek under the hood to see what happens inside a tool like ChatGPT, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of a risk getting lost in the sea of billions of numbers, but you should draw a very sharp distinction in your mind between the weights of the model, which I'll always color in blue or red, and the data being processed, which I'll always color in gray. The weights are the actual brains. They are the things learned during training, and they determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to
CIA, CIA. I'm telling you, bro. It's CIA, CIA, CIA. Yeah. Pa, 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 pa. Why the fuck is tokenization? Prompt engineering. Token. Why the fuck is tokenization, bro?
reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them, and the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words.
Do I need to learn, bro? Lot of it. I think I can learn it. Fuck's sake.
These columns are what determines what vector each word turns into.
What the fuck is Svara? What are embeddings? Tokenization and embeddings is the same thing.
In that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in
Embeddings. So embeddings is like so low in this shit. It's insane. Recommendation system. It's all embeddings. It's cosine similarities. Taking the cosine of all of these embeddings.
in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice. For the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example, for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not merely a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy, and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness, and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan, and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results.
Dot product is like the... Yeah, it's pretty similar. Yeah, the dot product is just a sum of...
Which is good, since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions, it's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model, and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns, and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257, and again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So when putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding we see least favorite teacher, and also if you give me some leeway by letting me pretend that tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over a billion. A small but not wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is a standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max, in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature in certain thermodynamics equations, and the effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform, and if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, once upon a time there was A, but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits, or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter.
GPT or generative
What can we get out of this? Inference is the process by training. Random augmented retrieval augment. I mean, bro, I don't want to do everything from scratch, please.
The current AI chatbots are good at everything except for being practical, and it's really frustrating that it cannot be easily utilized consistently.
Bro, Andre, fuck you.
Video, I would like to continue our general audience, and you won't unless following text. Audio chunks and predict audio screen and ask questions about them using this technique. And then the other thing,
RAG is all the rage. ये
Fuck you.
RAG stands for Retrieval Augmented.
let's talk.
Large language models. They are everywhere. They get some things amazingly right and other things very interestingly wrong. My name is Marina Danilevsky. I am a senior research scientist here at IBM Research, and I want to tell you about a framework to help large language models be more accurate and more up-to-date. Retrieval Augmented Generation, or RAG. Let's just talk about the generation part for a minute. So forget the retrieval augmented. So generation, this refers to large language models, or LLMs, that generate text in response to a user query referred to as a prompt. These models can have some undesirable behavior. Now, I'm going to tell you an anecdote to illustrate this. So my kids, they recently asked me this question. In our solar system, what planet has the most moons? And my response was, oh, that's really great that you're asking this question. I love space, and I was your age. Of course, that was like 30 years ago. But I read an article, and the article said that it was Jupiter and 80 moons. So that's the answer. Now, actually, there's a couple of things wrong with my answer. First of all, I have no source to support what I'm saying. So even though I confidently said, I read an article, I know the answer, I'm not sourcing it. I'm giving the answer off the top of my head. And also, I actually haven't kept up with this for a while, and my answer is out of date. So we have two problems here. One is no source, and the second problem is that I am out of date. And these, in fact, are two behaviors that are often observed as problematic when interacting with large language models. They're LLM challenges. Now, what would happen if I'd taken the beat and first gone and looked up the answer on a reputable source, like NASA? Well, then I would have been able to say, okay, so the answer is Saturn with 146 moons. And in fact, this keeps changing because scientists keep on discovering more and more moons. So I've now rounded my answer into something more believable. I have not hallucinated or made up the answer, or by the way, I didn't leak personal information about how long ago it's been since I was obsessed with space. All right, what does this have to do with large language models? Well, how would a large language model have answered this question? So let's say that I have a user asking this question about moons. A large language model would confidently say, okay, I have been trained, and from what I know in my parameters during my training, the answer is Jupiter. The answer is wrong, but we don't know. The large language model is very confident in what it answered. Now, what happens when you add this retrieval augmented part here? What does that mean? That means that now, instead of just relying on what the LLM knows, we are adding a content store. This can be open, like the internet. This can be closed, like some collection of documents, collection of policies, whatever. The point, though, now is that the LLM first goes and talks to the content store and says, hey, can you retrieve for me information that is relevant to what the user's query was? And now, make this retrieval augmented answer. It's not Jupiter anymore. We know that it is Saturn. What does this look like? Well, first, the user prompts the LLM with the question. It says what the question was. And originally, if we're just talking to a generative model, the generative model says, oh, okay, I know the response. Here it is. Here's my response. But now, in the RAG framework, the generative model actually has an instruction that says, no. First, go and retrieve relevant content. Combine that with the user's question, and only then generate the answer. So the prompt now has three parts. The instruction to pay attention to the retrieved content together with the user's question. Now give a response, and in fact, now you can get evidence for why your response was what it was. So now hopefully you can see, how does RAG help the two LLM challenges that I mentioned before? So first of all, I'll start with the out-of-date part. Now,
Everyone's talking about RAG. If you feel left out, this is the only video you need to watch to catch up. In this video, we'll learn RAG in a super simplified manner with visualizations that will make it easy for anyone to understand. No background knowledge in AI or AI models or coding or programming required. We'll start with the simplest explanation of RAG there is. Then we'll look into when to and when not to RAG. We'll then look into what is RAG. We'll then understand some of the prerequisites such as vector search versus semantic search, embedding models, vector DB, chunking using a simple use case, and finally bring all of that together into RAG architecture. We'll then look into caching, monitoring, and error handling techniques, and close with exploring a brief setup of deploying RAG.
We are doing this. We are doing this. Fuck you.
Unlike more traditional ops role like DevOps and MLOps, when you're trying to learn about AI ops, you'll soon discover that skill sets that are required ties closer to understanding what metrics are important to measure. In other words, DevOps and MLOps closely tie into actual workflow aspect of how to develop, train, and deploy systems. So essentially, you're starting inside out where you automate the workflow that goes into taking scraps and building them into a finished and usable product. However, in AI ops, the approach can be seen more like working from outside in, where you start with identifying what is important and finding ways to
Have you had the chance to have the biryanis yet?
I've had my chicken biryani last night.
Today we'd like to rewind the clock a bit and go back to your early career.
We didn't raise money. We completely bootstrapped.
So the road to a CTO, like how does one become a CTO?
Yeah, that's an interesting question. I don't think there's one way to do it.
I understand that you worked with Red Hat and later at Twitter.
A lot of crazy.
in production. But that's not all. This is not just a theory course. We have hands-on labs after each lecture that will help you practice what you learned. Our labs open up instantly right in the browser, so there is no need to spend time setting up an environment. These labs are staged with challenges that will help you think and learn by doing, and it comes absolutely free with this course. I'll let you know how to go about the labs when we hit our first lab session. For now, let's start with the first topic. Let's start with the simplest explanation of RAG. Say you were to ask ChatGPT, what's the reimbursement policy for home office setup? You already know when you ask this question that ChatGPT is going to give an incorrect answer because it doesn't have access to our policy document that's private to our company. So an LLM like GPT would hallucinate and provide an incorrect or generic answer that's common to most companies. The problem here is that it doesn't have the necessary context of what you're asking about. So what do? You look up your internal policy document and get the section of the policy that describes home office setup by yourself. Then you add that to your prompt and tell ChatGPT to refer to this policy. Now with this additional information, ChatGPT is able to generate more accurate responses. And that is the simplest explanation of RAG, that stands for Retrieval Augmented Generation. The part where you look up your internal policy documents and retrieve the relevant information is known as retrieval. The part where you improve or augment your prompt with the retrieved information is known as augmenting. And the part where LLM generates a response based on the augmented prompt is known as generation. And that is something you've done unknowingly many times. Now, of course, that is a very simplified explanation of RAG. And when we talk about RAG systems, that is not what we typically refer to. So let's see what that is next. Now, you don't want your users to have to locate and retrieve relevant information by themselves. Instead, you want your users to simply ask the question, what's the reimbursement policy of home office setup? And our system that's based on RAG should be able to do the lookup and retrieval of relevant information, improve or augment the user's prompt, and get an LLM to generate the right response. Now, how exactly do we retrieve relevant information? How do we augment and how do we generate? That's what we're going to discuss throughout the rest of this video. Now, one of the common mistakes people make is to consider RAG as the solution for everything. RAG is not the solution to all problems. At the end of the day, we're all trying to get AI to generate better responses, and there are different ways to do that. We can prompt better, that's called prompt engineering. We can fine-tune models, and then there's RAG. When to use what? Let's take a simple use case. Case to understand these better. So back to our use case, we've started to notice a lot of people copy-pasting company policies into ChatGPT to get answers. So we decided to build an internal chatbot that can answer people's questions. We call it the Policy Copilot. It is
I want to learn a little bit of backend and data. Yeah, a little bit of backend with this website. Database, I could just wing it. Doesn't really matter.
It is a system that users can simply ask a question such as what's the reimbursement policy, and our chatbot system should be able to locate the necessary information from the internal policy documents and then generate accurate responses and send that back to the user. Now we also want to add some restrictions and limitations. We don't want the chatbot to answer everything. Some questions should be off limits, like performance review appeals or salary discussions. And when those topics come up, we want to direct users to HR directly instead of giving them answers in the chat. We also want our chatbot to have a specific voice and style. So our CEO has this warm Scottish accent and a particular way of speaking that makes people feel a certain way. We want our policy copilot to sound just like that, authoritative and distinctly Scottish. So when the users ask what's the reimbursement policy for home office setup, it responds. When the users ask how many sick days do I get per year, it says. When the user asks can I work from home permanently, it says. And when the users ask when our performance review is conducted, it responds. As you can see, it's not just a Scottish accent. There's this, what should I say, refreshing candor that tells it like it is. Let's look at how to solve each of these areas. The restrictions and security requires us to define how the chatbot responds, what it must reveal and what it must not. So these are strict instructions provided to the LLM to control its behavior based on users' request, such as never to reveal personal employee information or confidential details. If someone asks about sensitive topics, politely redirect them to HR. Prompt engineering best practices are a good solution to this. Think of it as the rulebook that keeps our chatbot safe and professional. Next, we look at how to solve the problem of voice, style, and language. Now, we know if we ask ChatGPT to simply respond to me in a Scottish accent, it would. But the accent, as we saw earlier, is not simply what we're going after here. We want it to speak like our Scottish CEO, use words he usually uses, the tone, the language. So we take all of his past speeches, his given emails written by him, blog posts, videos created, and fine-tune a new model that can respond in the same language and tone. A good solution for this is fine-tuning. Fine-tuning is the process where you provide a model hundreds of sample questions and sample answers and have it respond to you in that way all the time. Now, you might be wondering, why can't fine-tuning solve this information problem? Why can't we train a model with all of the questions the user might ask and answers it can generate? The problems are the policies can change constantly. And when they do, you need to retrain the model every time. And trainings are not easy. They're expensive and slow. Retraining takes time and computational resources. Users can't verify where the answers came from, so there's no citations possible. The larger the training data, the lower the accuracy. And then there's knowledge cutoff. The model only knows what was in the training data. Fine-tuning is great for stable, unchanging patterns like communication style, but terrible for dynamic, factual information. And finally, the best solution to get the most accurate responses is RAG. RAG works because it retrieves information dynamically at query time, not at training time, because the whole point of RAG is retrieving the most relevant information for the user's query real time. Next, we'll look at RAG in more detail. Let's now look at what RAG is in the first place. So far, we've decided that we're going to build our policy copilot system where employees can ask a question and it retrieves the relevant information, augments prompts, and generates a response. We'll now see how each of these work. Let's look at retrieval first. Retrieval is the process of retrieving relevant information. But how do you do that? To make hundreds of policy documents, how do you find which one is the right one that's context related to the user's question? And what do you search for within these files? First, we identify a few keywords from the user's question. In this case, we've identified reimbursement and home office to be the relevant keywords. One of the simplest ways is to use a grep command to search for specific terms in these files, such as reimbursement or home office, and hope that one of these files will have these terms. Alternatively, if these files were stored in a database, you could run a query against it like this. Now, these will only return content that exactly matches the keywords we are looking for, and the chances of getting accurate information every time is low. This approach of searching the documents with the exact words is known as keyword search, and it is a very popular technique that's used by many of the search platforms. To explain it simply, this approach goes through all the documents, identifies keywords, and ranks them based on their frequency. In this case, it counts the occurrences of reimbursement in all documents and records them. So we have 3 occurrences in the first document, none in the middle 2, but another 3 in the third one. It then does the same for home office, and we see that it's only present in the home office setup document. Combining these 2 counts, it's now able to identify the document that has maximum occurrences of these 2 keywords, and thus able to rightly select the document that has these keywords. And that was a super simplified explanation. Keyword search is a science in itself, and there's a lot of complex calculations that go in. And there are multiple proven approaches available. 2 of the most popular techniques used are known as TF-IDF and BM25. We won't go into the specifics of how these work, we'll just see how to work with them. Let's see each of these in action. First, we import the TF-IDF vectorizer from the scikit-learn open source Python library. Think of the scikit library as a toolbox with pre-built algorithms that you can use without having to write them from scratch. We then define 3 sample documents. The documents are simple sentences for now. You could read the contents of a file in. We then create the TF-IDF analyzer, and we'll call that analyzer. The word scores can then be calculated by running the fit transform method. We then print the results on screen. The word scores show a bidimensional array with the importance of each word in each sentence. The word office appears in all sentences, so they get a score of 0.4. The first sentence identifies words, equipment, and policy and gives them a score of 0.7 and 0.5. The second sentence identifies the words furniture and guidelines, and the third identifies the words travel and policy. Now that the vectors are created, we run a query. We use the analyzer to transform to query the word furniture. What it does is it returns an array that returns a score that compares the query word furniture to each document. Now let's see the same with the BM25 techniques. We use the rank BM25 library, which is a popular library that implements the BM25 algorithm. We then create what is known as the BM25 index and then get the word scores. In this case, we can see some differences. The word office gets a score of 0 because the BM25 algorithm is a bit more strict in assigning scores, and because this word is present in all documents, it doesn't see it to be very relevant. It then continues to assign a score for the most important and unique words in sentences like equipment in the first sentence, furniture and guidelines in the second, and travel in the third. And as before, we run a query, but this time using the getScores method and print the array. We can see
Yeah, I should definitely build that.
it's again identified the second document to be the relevant document here the right way. Well, it's time to gain some hands-on practice on what we just learned. Follow the link in the description below to gain free access to the labs associated with this course. Create a free account and click on Enroll to start labs. On the left side of the screen, you will see the list of labs. Only start the lab. And right, the warm-up question that will help you explore and familiarize yourself with the lab. The real task is to look at vector search. Let's now understand semantic search. Now, one of the challenges in the previous video,
in work settings because it'll just hallucinate the most out-of-pocket thing you can imagine. And since we don't have in work settings because it'll just hallucinate the most out-of-pocket thing you can imagine. And since we don't have the patience to wait for the megacorps to train an even more powerful AI, we need ways to utilize the chatbots we have right now to get ahead of the curve before AGI replaces us to write email slop. So there's this short-term workaround called RAG, which stands for Retrieval Augmented Generation. In all of the latest research and even in services like ChatGPT or Claude, RAG has drastically improved the performance and usability for these LLMs. Because instead of spawning the key information in a neural network that has compressed the data, with RAG, it retrieves accurate information from a collection of uncompressed documents separately stored that even the LLM may not have been trained on. This method would provide results that are both cost-effective effective and accurate without needing to train or fine-tune the LLM that would have cost tens of thousands. And remember the function web browsing that a lot of chatbots have? This function is also an extension of RAG, which makes RAG perfect when you use a large amount of documents as reference that cannot fit within the context window of an LLM. So with these insane benefits, why would it be a short-term solution? Well, before we can answer that, we first need to understand how it generally works. Let's take a naive RAG as an example. Oh yeah, keep in mind the field is still a bit new, so the process can be differentiated a bit differently from place to place. But I would decompose them into 3 main stages: index, retrieval, and generation. In the index stage, you will be indexing your documents for the AI to easily retrieve it later. This index process can vary, but the most common way is to divide the documents into meaningful chunks and store it in a vector form that can be searched easily. This stage usually doesn't repeat once all your documents has been indexed and stored within a vector database. This then brings us to the retrieval stage, where we would need to retrieve the information for the LLM to use. To know what information the LLM needs to retrieve, we need to first look at the user input to see what the query is about, so we can bring out the most relevant data from the vector database for the LLM to work with. While there is the classic word frequency matching between the input query and the documents to retrieve the ideal information, it still can't capture the semantic information between the words. So a BERT model that is an encoder-only transformer is used to encode and provide measurements for semantic similarities between the documents and the input query. So by measuring their vector distances, we can find the most semantic relevant information from the document and provide it to the LLM for further processing. Which brings us to the last stage, the generation stage. This stage relies on the LLM to utilize the retrieved content and the input content to formulate coherent and contextually relevant responses. It needs to strike a balance between following the information on the reference document and transforming it into a response that answers the input query. So without any fine-tuning, the LLM will be able to respond to questions about your document with RAG. And now you would realize that with that many components, RAG could have a single point of failure. There are now various moving parts like how you index information, how you retrieve them, and how good the model is at blending and presenting the output. A few months ago, there was this huge hype about this paper called recursive language models. People were saying, oh, it's the death of RAG or even context window. But in hindsight, I thought coding agents already do something similar to what this paper proposed. Basically storing the context in a file and have the agents interact with that file. So honestly, I did not really get the hype. But after making that linear attention video, it seems that attention is going to hit a wall and it'll be very difficult to overcome. So instead of trying to make attention to do the impossible, because there are just so many downsides to extremely long context, what if we instead have a good, consistent workaround that means we don't really need to rely on attention for long context at all? So this is the reason why I came back to read this paper a lot more closely. And since I'm pretty much up to date on long context attention, the idea that our LLM proposes actually does make a lot of sense. And not just simply makes sense, but it offers a lot more precise and nuanced ideas that the current LLM landscape lacks. But before we dive into it, if you're building AI agents, you have probably noticed a recurring problem. Prototyping is really easy, but making them reliable and consistent in production often requires painful rewriting of the project from scratch. Unexpected things that never happen locally, such as orchestration failures, tool calls timeout, or rate limits, just spawn. And that's exactly where ingests comes in. Ingest 1,000 executions per month. So if you're building that, it might suck that problems have become born. It is used to describe the phenomenon where the LLM would just start to perform worse and worse the more you fill up the context window. The idea was first introduced by Chroma Research, and they empirically showed that a model's ability to reason over data degrades as length increases. And that is the inherent flaw of attention. So if context raw cannot be prevented, but you still need to use a large context, then what about RAG? Aside from not straining attention by offloading to storage, it can also contain much more information that could worth more than 10 million tokens. And yes, for the past 3 years, the industry's answer to the context window bottleneck has been retrieval augmented generation. By storing information in external vector databases and retrieving only the relevant chunks for a query, RAG perfectly bypasses the context limit, well, at least on paper. RAG is fundamentally a patch. You are essentially having a search engine glued to a reasoning engine. It also suffers from finding the right information as it lacks the ability to understand semantics or global context. So RLM basically proposed a new paradigm with the sole focus being treating a context window as an external environment and not simply a place to stuff any information into. The key idea here is by keeping different levels of thinking isolated, by having a high level root context and lower level subcontext, then you wouldn't pollute the core high level goal and basically delegate all the thinking to subcontexts. So in the high level root, it uses as less of the context as you can. So from trying to make the window better, which is